This is lecture 4, section 1.4 on homogeneous equations and vector subspaces. This is really just a review of some things we've done already, so it only should take a few minutes. So a homogeneous equation, for example, 3x1 minus 2x2 plus x3 equals 0, is homogeneous because when the variables are on the left, the number on the right is 0. And if it's a non-zero equation, at least one of the coefficients of one of the variables is non-zero. So you can always solve for one variable in terms of the other. In this case, the simplest thing is to solve for x3. x3 is minus 3x1 plus 2x2. So if you have any solution of the equation x1, x2, x3, x1, x2, and x3 is minus 3x1 plus 2x2. And we can separate this. Maybe I'll write it like this to make it as clear as possible. This is equal to x1, x2, minus 3x1 plus 2x2. So I'm writing like this just to try to make things very clear. I'm sort of lining up the x1s and the x2s. It would be like a 0 here and a 0 here. You can always add 0. So this is the sum of two vectors, x1, 0 minus 3x1, and 0, x2, 2x2. From the first vector, we can factor out the scalar x1, 1, 0, minus 3. And from the second, we factor out the scalar x2, we get 0, 1, 2. So the solution space of this equation is the set of all linear combinations of these two vectors. So x1 and x2 can be any scalars, any real numbers. And this is a subspace. This set of vectors is closed under vector addition and scalar multiplication. So for a homogeneous equation, we get always a subspace of our vector space. That's really the most important observation. And this is stated as a theorem. In the following way. The solution space of the homogeneous linear equation, a1x1 plus a2x2 up to an xn equals 0, is always a subspace of Rn. And notice, if this is the 0 equation, the 0 equation means that all of the coefficients are 0. Then the solution space, W, is in fact all of Rn. Because if each of these coefficients is 0, every vector solves the equation. Every choice of x solves the equation. So if the solution, if this is the 0 equation, the solution space is all of Rn. And if this is a non-zero equation, and some coefficient, a sub j is different from 0, you can solve for xj. It's also easy to check that if, let me use sigma notation, if summation ai xi is 0, I goes from 1 to n, and summation ai yi is 0, I goes from 1 to n, then if I take summation AI times xi plus yi, if I add the x and the y's, I goes from 1 to n, and I distribute, this is summation ai xi plus summation ai yi, that's 0 plus 0, which is 0. And similarly, if I multiply one of the coefficients, one of the variables by c, I can take the c outside, and again I get 0 plus 0 equals 0. So the set of solutions is closed under vector addition and scalar multiplication, and so is the subspace. That's the very simple idea that we have here. Yeah, that's really all there is to section 1.4. So we can stop right there.